In the last section of chapter 7, we are going to talk about difference in means. So we're going to talk about confidence intervals and significance tests. So just to review, when we're looking at a difference in means, we are looking at two different populations or treatment groups, which means we can have two different population means, so mu1 and mu2. We can also have two different population standard deviations, so sigma 1 and sigma 2. It also means two different statistics, x1 bar and x2 bar, and sample standard deviation, so sx1 and sx2. It also means two sample sizes, n1 and n2. When it comes to the conditions for a difference in two means, for the shape, which is normality, if the population distribution is normal, then the difference is normal. So you don't have to worry about sample sizes being high enough if the populations are each normal. If you do not know the shape of the population distributions, then their difference is approximately normal if both sample sizes are large enough. So that would mean that N1 has to be greater than or equal to 30 and N2 has to be greater than or equal to 30. For the center of our difference, so the mean, mu x1 minus x2, is just to subtract each mean. And again, this comes from randomness. So that can either be random assignment or random selection. And then the standard deviation for a difference in means is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And this is the 10% condition. So each sample size has to be less than or equal to 10% of their population. And again, I'm not going to make you check conditions. I did just want to review them though, because it's been a while since we've talked about difference in means. Okay? Very similarly to when we were doing a significance test or a confidence interval for a single mean. And there is either a t interval or a z interval, and then a t-test statistic or a z-test statistic. The same thing happens for a difference in means. So you can have a z-test statistic for a difference in means or a t. So if you are given population standard deviation, then your z-test statistic is x1 bar minus x2 bar over the square root of standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. All right, straightforward. However, because we are rarely going to be given our population standard deviation, we're going to have our sample standard deviation, we have to talk about a t statistic for a difference in means. So it is no longer referred to as standard deviation, it is now standard error. So the only way the formula changes is now it's just S1 squared over N1 plus S2 squared over N2. So it becomes sample standard deviation instead of population. So that leads us to our t statistic. So the numerator is not affected. So our numerator is still going to be x1 bar minus x2 bar. But now our denominator is the sample standard deviation 1 squared over n1 plus sample standard deviation 2 squared over n2. This also then ends up affecting our degrees of freedom. So because we are not required to have the same size sample for a test statistic, our degrees of freedom cannot just be n minus 1 because we could have two different sample sizes. So there is a new formula for calculating degrees of freedom. We are not going to use this formula because the degrees of freedom actually does not end up being a whole number. And there is a place on the calculator where you can find this, but we're not going to discuss it because we are going to go with option 2. And option 2 says that your degrees of freedom is the smaller of whatever n1 minus 1 or n2 minus the second sample size minus 1. So it's the conservative method, which is perfectly okay for our purposes. So whatever sample size is smaller, we use it for the degrees of freedom when we are performing a significance test. So confidence intervals are going to have a margin of error as large or even slightly larger than is what is needed. And then our p-value ends up slightly being bigger than the true p-value. But again, not enough to where it's going to cause major issues. So when it comes to then doing, we could also do a t interval or a z interval for a difference in means. We're mainly going to be doing t interviews. So we're going to do x1 bar minus x2 bar plus or minus our t critical value times our standard error, which is the square root of s1 squared over n1 plus s2 squared over n2. And the way we calculate our critical value, again, when we're identifying our degrees of freedom, we use the smaller between n1 and n2. All right, so now let's talk about writing our hypotheses for our significance test. So our null hypothesis is always going to be that mu1 minus mu2 is 0. The other way you can write it is also that the null hypothesis is that mu1 equals mu2. So it's either that their difference is 0 or they're equal to each other. And then you're going to choose your alternative hypothesis based on the wording of the problem. And that's, again, it can either be that their difference is greater than 0, their difference is not 0, or their difference is less than 0. You can also say mu1 is greater than mu2, mu1 does not equal mu2, or you could say mu1 is less than mu2. So let's take a look at some examples. So there's observational studies suggest that moderate use of alcohol by adults reduces heart attacks and that red wine may have special benefits. One reason may be that red wine contains polyphenols, substances that do good things to cholesterol in the blood and so may reduce the risk of heart attacks. In an experiment, healthy men were assigned at random to drink half a bottle of either red or white wine each day for 2 weeks. The level of polyphenols in their blood was measured before and after the 2-week period. Here are the percent changes in level for the subjects in both groups. And then dot plots of both distributions showed no outliers or strong skewness. So we're going to construct and interpret a 90% confidence interval for the difference in mean percent changes in polyphenol levels for the red wine and white wine treatments. Does the interval suggest that red wine is more effective? Explain. So first, we are going to define our x1 and our x2. So I'm going to let x1 be red wine and x2 be the white wine. The next thing we have to do is calculate our sample statistics. So I have my list of data, which means I can calculate their mean and standard deviations by entering the data into the list feature of the calculator. And again, as you're typing these in your calculator, you do want to pay attention that you are typing them correctly and that you are not forgetting any decimals or any numbers altogether. Okay. So for our first list, which is red wine, we get a mean of 5.5 with a sample standard deviation of 2.52. And our second list has a mean of 0.233 and a sample standard deviation of 3.29. And then because we are doing a confidence interval, I need to now calculate my t-critical value. So we're going to second bars and we're going to do INVT. For the area, so we're doing a 90% confidence interval, so remaining area to 100%, which is 10 divided by 2 is 0.05. And then for degrees of freedom, both of our sample sizes are the same. They're both 9, so 9 minus 1 gives us degrees of freedom of 8. Then we ignore the negative and we get 1.86. So now I'm going to set up my interval. We're going to have 5.5 minus 0.233 plus or minus 1.86 times the square root of 2.52 squared over 9 plus 3.29 squared over 9. And again, I do like to do this in steps. So I'm going to multiply the 1.86 times my square root. And I'm going to do my subtraction. So we're going to end up with 5.267 plus or minus 2.569. So now I'm doing my plus and my minus. We're going to get 2.698. And then when we add, we're going to get 7.836. So instead of writing our traditional sentence where it says we are 90% confident that the true difference in mean percent changes in polyphenol levels for red and white wine treatments is between, I'm going to just go ahead and answer the question. Does the interval suggest that red wine is more effective? So because we specifically looked at the difference red wine minus white wine, and every number in my interval is positive, the interval does suggest that red wine is more effective. If I had had a negative number at any point, that would have meant that white wine was more effective at some point. So we're going to say, yes, the interval suggests red wine is more effective because the interval only contains positive values. In our next question, we want to know if increasing the amount of calcium in diet reduces blood pressure. So we have data on 21 healthy black men, and they were randomly assigned to two groups. 10 took a calcium supplement for 12 weeks, and then a control group of 11 men received a placebo. And it wanted to look, the response variable was a decrease in blood pressure after the 12 weeks in millimeters for mercury. And an increase actually appears as a negative number. So we have group 1 and group 2s, and we want to know, does the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo? So again, we're going to have to define our X1 and our X2. So I'm going to let X1 be group 1 and X2 be group 2. So for the null hypothesis, it is always that they're equal. For the alternative, so we want to know if a calcium supplement reduces blood pressure, which would mean that people's mean average in group 1, because a positive number represents a decrease, we would want their mean to be greater than the group who took the placebo. So just because it says the reduces, we don't actually want a less than, because reduces is actually signified by a positive number here. So we need to calculate all of our statistics. So again, we're going to have to enter all of our data into the list of our calculator. So for group 1, they have a mean of 5, and their standard deviation is 8.74. And then for our second group, their mean is negative 0.273 with a standard deviation of 5.9. So a negative mean here actually means that there was an increase in their blood pressure instead of a decrease. So when we calculate our test statistic, we're going to do 5 minus negative 0.273, and then all over the square root of 8.74 squared over 10 plus 5.9 squared over 11. And we're going to get a test statistic of 1.6. So the way we calculate our p-value, we're going to go to TCDF. Our lower bound is going to be 1.6. Our upper bound is our 9s. And then for our degrees of freedom, our smaller sample size is 10. So our degrees of freedom are going to be 9. And we're going to get 0.072. It does not state anywhere in the problem about a specific level of significance, so we're going to go ahead and use 0.05. So this is greater than an alpha of 0.05, which means we are going to fail to reject the null hypothesis, which means there is not enough evidence to show taking a calcium pill reduces blood pressure. All right, so next thing we're going to talk about is the relationship that exists between confidence intervals and significance tests. So we did talk about this with proportions. We talked about specifically if we were doing a two-sided significance test, so our alternative hypothesis was does not equal, a confidence interval where the percentages of your significance level and confidence level added to 100% should support each other. So the example that we're going to look at has to do with prenatal care and whether or not women who were part of this program gave birth to babies with a higher average birth weight versus those who did not. So we have a random sample of hospital records indicating that the average birth weight for 75 babies born to mothers enrolled in the program was 3,100 grams with a standard deviation of 420. And then for women who did not take part, there were 75 also babies, and their average birth weight was 2,750 grams with a standard deviation of 425. So we're trying to figure out if mothers who participate in the prenatal care program have babies with a higher average birth weight than those who don't. So we're going to look at a 99% confidence interval. So thankfully, I don't have to calculate any statistics here because it's given to me. I still have to define X1 and X2. So I'm going to have X1 be enrolled in the program. So enrolled, and then X2 would be not enrolled. So we have to find our critical value. So we go to INVT. Our area is going to be 0.005. And then our degrees of freedom, 74. Because again, our sample sizes are actually both the same. So ignoring the negative, 2.644. So we're going to do mean 1, 3,100, minus mean 2, 2,750, plus or minus 2.644 times the square root of 420 squared over 75 plus 425 squared over 75. So 3,100 minus 2,750 gives us 350 plus or minus 182.423. So we get 167 to 0.577 to 532.423. I'm not going to interpret the confidence interval here because we're going to do the interpretation at the end after we've done our hypothesis test. So in B, we want to conduct our significance test to see if there's a significant difference in mothers who participate in the prenatal care program and those who don't. So our null hypothesis is going to be that mu1 equals mu2. And our alternative hypothesis is going to be that mu1 does not equal mu2. So it does say significant difference. We're not trying to do greater than or less than. We also can't compare a confidence interval in a significance test unless the alternative hypothesis is does not equal. I'm not redefining X1 and X2 since it doesn't change from the previous problem. So we still have 3,100 minus 2,750 in the numerator, and then my standard deviation or standard error in my denominator is the square root of 420 squared over 75 plus 425 squared over 75. So we're going to get a test statistic of 5.07. So when we go to find our p-value, we're going to go to TCDF. Our lower bound is going to be 5.07. Our upper bound is our 9s. And then our degrees of freedom is 74.
Price increases.
So you get 1.423 E -6, and then because the alternative hypothesis does not equal, this needs to double, which becomes 2.846 e -6, which if you want to write as a decimal is 0.00002846, which is going to be less than our alpha of 0.01, which means we reject the null hypothesis.